Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. Let's continue with the 9th one. This lesson is divided into several parts. Efficiency is a very important aspect in calculating fins. Let's see how we define it and how we calculate it. Let's use a chip with a heatsink as example. We will analyze the central plane. The maximum driving force for convection is the temperature difference between the base at x equal to 0 and the fluid. Notice that the temperature of the base of the fin T0 is the same than the prime surface in contact with the fluid. Hence, the maximum rate at which a fin could dissipate energy is the rate that would exist if the entire fin surface were at the base temperature. However, since fins have a finite conduction resistance, a temperature gradient must exist along the fin, and the above condition is an idealization. The fin heat transfer rate is lower than the maximum. A logical definition of fin efficiency is therefore the ratio between the real heat transfer rate and the maximum heat transfer rate. What is the efficiency for a very long fin? For a very long fin, it is easy to integrate the excess temperature along the fin. We have already done this integration in the video about the calculation of the heat transfer rate. Taking into account the definition of efficiency. Making simplifications, the efficiency of a very long fin is 1 divided by mf times Lf. The efficiency of very long fins is very small and tends to 0 as Lf tends to infinity. What about the fin efficiency for other boundary conditions? For the fin of adiabatic tip, we can proceed in the same way. After the definition of efficiency and the expression for the fin heat transfer rate for a fin of adiabatic tip, and rearranging terms, we obtain the expression of the efficiency for case B. The next type of fin to be analyzed is the one with convection in the tip. It has the more complex expression for the temperature distribution, and, therefore, the more complex expression for the efficiency. If the efficiency is height, this efficiency can be calculated with a simplified formula. For a fin with a prescribed temperature in the tip, there is no point in talking about efficiency. What about fins of non-uniform cross-sectional area? There are many fins of non-uniform cross-sectional area. In that case, you must look for the efficiency of the fins in tables or graphs. What about the heat transfer rate of a fin surface? Let's analyze the heat sink on an electronic chip. For doing this, we need some definitions. Prime area is the area not covered by the fins. Its temperature is T0. With the one-dimensional flow hypothesis, the prime area is at the same temperature as the base of the fins. The heat transfer rate for this surface is the result of applying the Newton's law. The area of fins is the area of one fin times the number of fins. Using the definition of efficiency, the heat transfer rate of the fins will be the maximum heat transfer rate multiplied by the efficiency. The heat transfer rate of the fin surface is the sum of the one for the prime area and the one for the set of fins. Taking a common factor, we see that we can apply Newton's law to a fin surface where the heat transfer surface is the sum of the prime area and the area of all fins multiplied by the efficiency of the fins. As shown in the figure, there are many ways for joining fins to a surface. In fin theory, we have assumed that there is no discontinuity at the fin base. However, depending on the type of joint, the thermal contact may not be perfect. In such a case, there will be a contact resistance at the base of the fin and a temperature drop at the base. Using the electrical analogy, you can see that the new thermal resistance is the specific contact resistance divided by the cross-section of the fin. The heat transfer rate for a fin with contact resistance is lower than that of the same fin without contact resistance. For the definition of the efficiency, we keep the expression of the maximum heat transfer rate, being all the fin surface at T0. Simplifying the expression, we get the formula for the calculation of the efficiency of a fin with a contact resistance in its base.